One of the most important concepts that we have in statistics is that of the sampling distribution. So let's talk about it. Statistics vary for different samples, so a statistic is a variable. You'll recall that parameters are not variables, they are constant. But a statistic varies simply because when we take a random sample, we're going to have a different statistic for every random sample that we select. The distribution of a statistic is called a sampling distribution. We've been talking about the distribution of scores, but now we're talking about the distribution of statistics, and why not? Scores are variable, statistics are variable. Both of them have distributions. We have a special name for the distribution of a statistic, and that is the sampling distribution. An example of this is the distribution of the sample mean. That's a sampling distribution. Let's see an example of this. If you want to follow along, I'm going to be using the file sampling distribution of mean. That's an R script, and that's going to walk us through how this works. Okay, we're going to start off with the common example, at least common to us now in the last few presentations, of the height of females in the United States. The mean is 64.1 inches. The standard deviation is 2.75 inches. And let's call up again our graph to show the distribution of those scores. Now this distribution represents the distribution of female heights. So these are the original scores. But now here's what I'm going to do. I'm going to take samples of size 50 and I'm going to do it over and over again. So I'm going to take a sample of height of size 50 and I'm going to calculate the mean for that. That mean happened to be 64.3. Notice that it's not quite the parameter. The parameter is 64.1. But if I was doing research, I wouldn't have access to the parameter because I would not be able to measure the height and collect the heights of every 20 to 29-year-old female in the United States. So instead, I might take a sample, say size 50, and then measure the heights in that sample and look at the mean. And in this case, we would be pretty close, 64.3 instead of 64.1. Now, you know, if I took another random sample of size 50, I'm going to get different results. That's one of the concepts we've been working at here, is that every time we take a sample, we will get a different result. So let's do this 1,000 times. Let's 1,000 times take samples of size 50, and we're going to calculate the mean of each sample, and I'm going to keep track of those so that when I'm done, I'm going to have 1,000 means. Each mean comes from a sample of size 50. All right, let's look at the histogram of those means. There it is. Well, just like our original distribution, we see that we have a bell-shaped curve, a normal distribution. So originally, in the distribution of heights back here, we had a normal distribution. And when we take the means, each from a sample of size 50, we also end up with a normal distribution. Some things are similar to our original distribution, but some things are different as well. Look at the range of our original distribution. It looks like the heights begin somewhere down around 55 and they end somewhere up around 75. Actually, most of the heights start about maybe 57 and end around 73. The tails of those distributions are pretty flat by the time they get to 55 and 75. So let's roughly say a range here of about 55 to 75. That's about 20 inches. Look at this one. This, they seem to start right around, say 62.5, and they go up to about 65.5. That's not 20 inches, that's 3 inches. So when we take multiple random samples and calculate the mean for each sample, the standard deviation is going to be a whole lot less because we have a whole lot less variability than it was back here when we had our original sample. Here the range was from about 55 to 75, or about 20 inches, and here it was only about 3 inches. So one thing we've learned about sampling distributions of the mean is that they have less variability. They're more compressed than the sampling distribution of the original population. What about the mean of these means? Well, back in the original population, the mean was 64.1. Look at the mean of these means. It's about the same. And in fact, the mean of means is the same as the mean of our original population. So if we look at those two basic ideas, mean and standard deviation, the standard deviation of the sampling distribution of means is substantially smaller, a lot less variability. But the mean stays the same. The mean of the means is the same as the mean of our original population. We can actually even model this, and I'm going to superimpose a normal distribution in which I've set the mean as 64.1, which was the mean of our original sample. Let's take a look. There it is. Sure enough, it fits very nicely to use the mean of 64.1. But for the standard deviation, I use something a whole lot smaller, and we'll talk about that more, and I'll define it a little bit more precisely in upcoming weeks. But for now, notice that the mean stayed the same and the standard deviation was substantially less. A statistic is unbiased if the mean of the sampling distribution is equal to the parameter that the statistic is estimating. Well, what did we just look at as our statistic? We looked at the mean, correct? What is that supposed to be estimating? It's supposed to be estimating the mean of the population, which is the parameter, the mean. Were those two means equal? Did the mean of the sampling distribution equal the mean of the parameter? Yes. Not all of the individual sample means equaled the mean of the parameter. They varied. Remember, they had a variability of about 3 inches. But if you took the mean of all of those means, that was equal to the population mean. Therefore, we say that the mean is unbiased because the mean of all sample means is the mean of the population. That's a very good property for a statistic to have. We would like to know that if we do research over and over and over again, that on average, we're going to get the right answer. Statistic stability. The standard deviation of the sampling distribution indicates our stability of our statistic, or how consistent we are. Notice that the standard deviation of the sampling distribution of the mean decreases with increased sample size, thus indicating increased stability. As we got a sample size of 50, we noticed that the standard deviation of those means was decreased. And in fact, if I had increased the sample size even more, there would have been even less variability in the sampling distribution. So when we look at the sampling distribution, we want to look at the mean and the variability to make sure our statistic is unbiased and that it gets more and more consistent the larger the samples we obtain.